with any luck. Listen, ladies and gentlemen, it's a very great pleasure, and indeed it's an honour to introduce tonight's speaker, a speaker that I consider to be the best speaker around. I barely need to introduce him. Star of morning television, star of all the top TV programmes on astronomy. It's our own Professor Alan Fitzsimmons, and Alan is going to tell us, did it move? Or do we still need to have, what do you call the guy that starred in that film? Do we still need to have his telephone number and Alan's call list? Alan, Professor.
So, first of all, I've tried to lower the volume to stop the echo so much. Can you, I don't think I've worked. Can you still hear me okay back? Okay, thank you. Well, yeah, that's been fun. 9 days. I can't believe it still. I'm going to give you a qualified answer by the end of this talk as to moving an asteroid if we do it. But of course, the primary subject of my talk will be the plan for the NASA DART mission and what we know has happened. So I'm basically going to go through very briefly, as you've heard it many times, the need for planetary defence and why we spend time doing this. I'm going to talk about the particular type of technology that DART was designed to test, the kinetic impact of technology, and why we need to test it. We'll talk, of course, about the DART mission and look at what happened on impact night just a week ago on Monday and look at the first results that we've seen. And then give you a taste of what's next, not only for this particular project, but what's coming up beyond it. So let's cut to the chase. DART was successful. Here's the last 5 minutes of the existence of the DART spacecraft speeded up. In fact, all the images are there. It was sending back to Earth 1 image per second because it was taking 1 image per second. And as you can see, the target asteroid Dimorphos is really slowly growing in size and then grows very big very quickly until we get those final images just before impact. And this, by the way, is the slide where we all cheered. Not because of the tremendous images before anything, but this image taken 1 second before impact could not be fully transmitted if you only got the first few lines of the image before DART could not transmit it anymore because it did not exist anymore. And that's when we started cheering, when we didn't get a complete image anymore. So why did we build DART and why did we fly it? Well, first of all, planetary defence. We know the Earth has been hit by asteroids and comets in the past. And if we do nothing about it, it will be hit again. And to help us cope with this, primarily NASA, but now ESA is also getting in the game. NASA has built and funded a suite of survey telescopes which scan the sky every night, looking for these moving faint dots of light, which are quite often asteroids that can come close to our planet. And the 2 surveys we are sorry, I just realised I didn't put titles on. The 2 telescopes that we've primarily been involved with here at Queen's is this telescope, one of these telescopes, this is the Atlas project, which is now a suite of 4 half-metre telescopes operating right now in, it's clear, in South Africa, and at about midnight tonight, one in June will take over, and about 6 o'clock this morning, South Africa will close, but the 2 telescopes in Hawaii will take over, so we have 24-hour coverage of most of the night sky, once a night with these telescopes. We also have pan stars over here, until the Moving Observatory gets going, still the largest digital camera in the world, 1.8 billion pixels, and that's how big your camera is, with a kind of medium-sized astronomer, I like to believe, standing next to it for scale.
So these telescopes are working every clear night at their observatories looking for faint objects, and they find them every clear night, pretty much. Here's the list as of, I think this is actually from last week, I should have updated it. Oh, hello. Sorry, I cut and paste the slides, and what you see behind here are all the institutions currently involved in the DART mission, so sorry about that. But if you ignore the scrolling and just look at this slide, here's the number of asteroids we're discovering in total that can come in the Earth as a function of time. And you can see we started taking off a little bit in the 1990s when we started using digital detectors on telescopes, and now we are discovering, on average, many new near-Earth asteroids every night. And in fact, at the beginning of last week, the week of the dark impact, we reached over 30,000 known asteroids that could come close to our planet. And as I said, at some point, we're going to find the one that's going to hit us, going to be the first sizable asteroid to hit us in the future. It might not be in the next 100 years, it could be in 200 or 300 years, but we will find it. And what do we do about it? Well, we've got two choices. Here's the plan. We find these asteroids, we discover them, we track them, we assess how likely they are to impact our planet, and we do one of two things. We do nothing. Yeah? That's, how can I put this? The political approach. And do nothing, eventually it will hit us. Or we can try and deflect the asteroid. We can try to deflect the asteroid and hit it way before it hits us. And we nudge it, we change its path around the sun slightly, and that will move it from a trajectory which, instead of hitting the Earth at some point in the future, means it passes us safely by. So the point of planetary defence is to identify these asteroids, it's to track them, assess where they're going, and if we do find one on an impact trajectory in the next 100 or 200 years, deflect it so it will not cause us. And this kind of puts asteroids in a particular category of natural disasters. It's the only natural disaster we can stop. We can warn ourselves about the incoming hurricanes, we can take precautions if we're living in an earthquake zone, which basically don't live in an earthquake zone, and do many other things like that. We can even keep an eye on that volcano over there on that next island and make sure there isn't too much smoke coming out of the top of it. But an asteroid impact is the only thing we think we might be able to prevent a natural disaster, something that humanity has never been able to do up to now. Now, there have been many different ideas about how we might cause this deflection. And certainly, so I've just explained, I've been working in this field for almost 20 years now, kind of maybe over 20 years. But it was about 18 years ago that I first sat on a panel at the Space Agency looking seriously at the various different techniques we might try. And the idea the best technology we had was effectively the simplest one. If you want to move something, just knock it out of the way with something else. And that's the idea of a kinetic impactor. The idea is that you take your spacecraft and throw it at high velocity onto an asteroid. Because in physics, we have something called the conservation of momentum. It's one of the foundations of the laws of physics as discovered by Isaac Newton, and it works. The idea is that the momentum of an object is given by its mass, how many kilograms does it weigh, multiplied by its velocity, how fast is it going. If you have a bigger mass or bigger velocity, the momentum, that number is bigger. And that momentum cannot disappear. It must be conserved according to fundamental laws of physics, which, funnily enough, over the past week I've been teaching our first year physics students, sometimes in this very lecture theatre. So what you do is you ram your spacecraft very fast into an asteroid. And now, when you do that, the spacecraft is no longer there. You know, it's probably not just going to stick to it like a sticky ball. It's if you run it fast enough, the spacecraft will be destroyed. But the momentum of the spacecraft will be transferred to the asteroid. So the asteroid, although it's much bigger, will get that extra bit of momentum. It's much bigger, so the change in the velocity of the asteroid will be much smaller, but that product will be the same. Now that's the basic idea of a kinetic impact. So it's pretty much cosmic billiards. Yeah? There's your cue ball, there's your red, you want to hit the red with the cue ball. But there's an extra factor. There's an extra factor that no matter how sophisticated we do our calculations, that we had no idea what that extra factor will be. And it's this. When you hit the asteroid with your kinetic impactor spacecraft, then that's got to send out lots of bits of asteroid. We know that's going to happen because we can see craters on asteroids and the moon where there were bits of rock there and they're gone because they were thrown out in the impact of the object that made that crater. And we also see even in experiments on Earth with small-scale experiments shooting small projectiles at high velocity into rocks and sand and so on. So we're going to get lots of stuff going out that way. And conservation of energy still works. If you throw out bits of rock with some total mass going this way, some velocity, that will also give you conservation of energy, means you get an extra kick that way. So in theory, your kinetic impactor should be better than just using the spacecraft by itself. And we define how good a kinetic impactor is by this number beta. This is the big number in planetary defense. How efficient would our spacecraft be at moving an asteroid? Beta basically tells us what's the momentum we actually give, the extra momentum we actually give the asteroid, or the change in momentum we give the asteroid, divided by the original momentum of the spacecraft. If we don't eject anything, and we only have the momentum of the spacecraft, that number would be 1. So this shows us what we need to do, what we need to determine. This number we call beta. If beta is 1, that means that when we hit an asteroid with a spacecraft, there isn't an ejector, we hit the asteroid and the asteroid moves this way. Just we give it a small nudge. If we're lucky and we eject a moderate amount of ejector going this way, then the asteroid gets a bigger nudge. If we end up giving with a very large amount because we eject a huge amount of material from the impact point, the asteroid will move even more. And depending on what numbers you put in your calculations, beta could be at least anywhere from 1 to 6. We have no idea how efficient a kinetic impactor might be. In fact, some ideas would have it less than 1. Because if you put a spacecraft hitting here, and the shock wave goes through the asteroid and jets stuff out the other way, then that moves the asteroid back this way. And it will actually be less efficient than what we expect. So there's no... Scientists looking at impact physics have done these calculations literally for a couple of decades, and there's no clear answer. It depends on how the asteroid will respond to the impact, what is the structure of the asteroid, how does the energy and the momentum get transferred. There's so many variables, so many things that we don't know. All we can say is that beta should be between about 1 and 4 larger, but we don't know where it will be. So this was the plan as formulated and then submitted to the space agencies back in 2016. We were looking at a 2 spacecraft mission. From NASA, we have DART. And DART would intersect a small asteroid, it's a kinetic impactor, and hit it in 2022. On the European Space Agency side, we have HERA, and HERA would run, instead of going straight through the system at high velocity, it would rendezvous with that small asteroid and measure the true effects of that experiment, if you like, in deep space. Now, originally the plan was that HERA would launch before DART and would be there when DART impacted. That didn't happen. We didn't get the funding for HERA initially, but we did get it 3 years later. Too late to rendezvous with the asteroid target before DART arrived, but as you see, we'll be there and still doing great measurements in a little while. So let's go to DART. This is one of the simplest interplanetary spacecraft ever launched. No spacecraft is simple, right? I mean, don't ask me to build one. I struggle with IKEA building bookcases. But what we've got is something the size of a kind of a large vending machine with solar panels to provide energy. We have navigation on there. We have an ion engine, which in the end we only use for a small amount of time. The one instrument on board is Draco. It's basically a version of the same camera that was flown on the New Horizons spacecraft to Pluto in 2015, because you don't want to put any other instruments on there. All you want is a really good camera to make sure that when you can see your target and you can get there. And because of that, we also have some highly sophisticated processing power, or computer processing power, because DART, in the final stage of the mission, will be steering itself. So, that's DART. The target is this. Here's 3 images of the sky being blinked as taken from the Space Watch telescope in 1996. And in these 3 images, it's a negative image, so stars appear black against a kind of a greyish sky background. But you can see within this little oblong box I put on here, a little dot of moving light. These are the discovery images of an asteroid we call Didymos, or was subsequently known as Didymos. Discovered on the 11th of April 1996. Now, at that stage, we hadn't even really seen any kinetic impactors. We hadn't discovered, we hadn't designed or submitted DART. What made Didymos a really good target to test kinetic impacted technology? Well, 7 years after its discovery, Didymos made a close flyby of Earth, and it was studied using telescopes on Earth. In particular, it was studied using the now sadly defunct Arecibo radio telescope, which is used for planetary radar studies, or was used for planetary radar studies of near-Earth asteroids. When asteroids come close enough, you actually send out very strong, very powerful radio wave pulses towards your target, and then get the reflections back. And here's a sequence of images of Didymos taken on the 23rd of November in 2003. So it's a sequence of images. Each image is separated by about 10 minutes or so. Yeah, I think it's about 10 minutes. Maybe it's a bit longer, maybe it's about 20 minutes. But the important thing is that here's Didymos. We can see the reflection of the radar pulses coming from the surface of that near-Earth asteroid. And immediately from this, we can tell it's about 800 meters across. But in each radar image, there's a little extra golden line. Here it is. And as you look at the sequence of images, it's moving further and further from Didymos. This is the moon of Didymos. This is an asteroid that has its own moon. And in fact, Didymos was one of these asteroids that was studied by Arecibo and also the Goldstone antenna, where we're doing a survey of asteroids flying close to our planet. It's kind of let us know that about 15% of near-Earth asteroids are binary asteroids. There's not just one asteroid there, there's 2 of them. So anyway, we can see this. Impressively, it wasn't just seen from the radar, because
in the Czech Republic, there's an astronomy group that are real experts at measuring how fast asteroids rotate. And when they just measure the brightness as a function of time and overlay them, you can get all kinds of wiggly lines like this. But if you kind of sort them out, what you find is that first of all you can measure how fast the main asteroid, that central asteroid, rotates, and it rotates about once every 2.25 hours. It's spinning really, really quickly, this Didymos. But when you take that out, that signal out of the rotation of the central asteroid from this data, what you see is something looking like this, where once every just under 12 hours, the light from Didymos itself dims a bit and then comes up. And then actually about 6 hours afterwards it dims again. This is caused by the moon of Didymos moving in front and behind that main asteroid. This is what we call an eclipsing binary system. This is very common, well not that common, but you see this in many stars, where we have two stars orbiting close to one another, you see this kind of pattern. Well, here we have it in front of an asteroid, where we see the moon disappear. We're going in front of the asteroid and causing a dim in the total amount of light, and then when it goes behind it. And as you can see, the orbital period here, determined from these data, was just under 12 hours. In fact, we only refine that, so it's to 11 hours 55 minutes. Now, the amazing thing about this is that, apart from those radar images, this is the only evidence that that moon exists. We can't see it from Earth. It's far too close to its parent asteroid, and they're separated by far too small distance to actually see it as 2 points of light, even from the Hubble Space Telescope or using adaptive optics on telescopes on Earth. Because this is the effective size of the system. This was a mock-up kind of we had before the DART mission. That we had the primary asteroid Didymos, 780 meters across. We have its moon, which we later called Dimorphos, 160 meters across, and the separation between the centre of Dimorphos and the centre of Didymos is just over a kilometre. Really, really close. If you want to see how close it is, here's Belfast. Okay, so here we are, where are we in Queens? Here we go, oh, there's Queens over here, there's the city hospital, there's the city centre, and let's dump down the asteroid system of Belfast. Not in real life, that's a bad thing, that's what we're trying to avoid. And you can see, actually, this is a pretty small scale system for the scale of the solar system. It really is quite small. But this binary asteroid makes this system a perfect test for kinetic impact of the target, because we know that Dimorphos orbits Didymos once every 11 hours and 55 minutes. And the idea is, without kinetic impact, not to hit Didymos, but hit Dimorphos and change its orbit. In that way, we can measure how much we can move an asteroid in a very safe way, because we have no risk. We've done the calculations, there's no risk of changing the orbits of both these asteroids around the Sun so it hits the Earth. All we're really doing is changing the orbit of Dimorphos around Didymos. Now, if we do this, how are we going to measure it? Well, remember, we can see Dimorphos when it's close to the Earth, and Didymos when they're close to the Earth, going around each other from these little dips in the brightness. We can also get radar if it's working at the time. Oops. We send our DART spacecraft into the system at high speed at just over 6 kilometers per second. It hits Dimorphos and gives it that kick. Not much of a kick. You know, we're following something the size of a vending machine against something the size of a small mountain. It's not going to do a lot, but it will do enough. We're only looking
forescore deflection. And if beta equals 1, if we get at least as much momentum, oh, is that my time? No. If we get as much deflection as just from the spacecraft alone, if this number equals 1, we would achieve that water appeared by 7 minutes. And we can measure that using telescopes on Earth. And we'll know we can move an asteroid. So here's the aim for the DART mission. These are the level 1 goals of the DART mission. So first of all, number 1, impact Dimorphos. DART. You know that, right? Well, that was the plan. That was the thing. Right? This is what we promised. The team promised NASA it would do. We would change the binary orbital period, and DART had to be designed in such a way that it would cause a change of at least 73 seconds. Now, why 73 seconds? Is because looking at the quality of the data we can gather with telescopes on Earth, we knew we would have an accuracy after, say, 2 months of measurement after the impact of about 73 seconds. So if we change the orbital by at least 73 seconds, then we'll be able to measure it. Measure the period change. In fact, we should have an accuracy of within actually about 10 times better, about 7.3 seconds. And then using these measurements of period change, calculate this beta factor. Calculate how efficient is a kinetic impactor at moving an asteroid. So, that's the level plans, and as you all know, DART launched successfully in November last year. I hope I spoke this the right point, yeah, because there was lots of seconds beforehand. But from Vandenberg, I wasn't there at the launch, but I know people that were, and it was nice. It was at Vandenberg. Actually, the problem is it was at Vandenberg Air Force Base, so if you weren't American, pretty much you weren't allowed on the US Air Force Base anyway. But it all worked well, and in fact, 55 minutes later, we could see the upper stage of the rocket was on the preliminary trajectory for DART, and this is the video of DART being released on its interplanetary trajectory to go and impact Dimorphos. It's not a straight line though. When you launch anything into interplanetary space, you're going around the Sun. So here's a graphic showing the orbit of Earth and then the orbit of Didymos. And here we have the launch of DART, and it shows the trajectory that DART was launched on. You can actually see that DART never actually gets that far from Earth in its trajectory, but the whole point is that it comes around here as Dimorphos is now coming in and Didymos are coming in towards the Sun, and if we get the trajectory just right, we get an impact on the 26th of September this year. Notice one thing about the video, I don't know if everybody noticed. During the closest approach, DART is actually in front of Dimorphos and Didymos. So, although from the perspective of graphics and everything else, we can say, okay, we took the spacecraft and slammed it into Dimorphos. Actually, what happened is we put DART in the way and let Dimorphos run into it. But in terms of relative motion, the two things are equivalent. Okay. Well, everything went fine on the approach. What did we expect? Well, we expected about a month before encounter that we would start imaging Didymos from the DART spacecraft, and that's actually what happened. As planned, it was quite close, so you had to sum up a lot of images to see Didymos and Dimorphos at that stage, but we could see it. From 10 days out, we had continuous contact, continuous communication with DART. Up until then, we only need to contact it once in a while to upload commands, check the trajectory, maybe have the trajectory course manoeuvre, and download images that we've taken. 8 hours before encounter, this is the so-called pre-terminal phase, this marks the last point at which we really want to do anything. And at a point, actually one thing I'll point out is that the day before impact, on the 25th, we had the opportunity for one more trajectory course correction. It wasn't done because we were assured by the navigation team that if we did nothing, we would hit Dimorphos. So we didn't do anything. And then at 4 hours, we can only still see Didymos. In the camera, in the powerful Draco camera on board, we can only see the point of light that is Dimorphos. But at 4 hours, we switch on the autonomous smart nav system, and at that point, it's up to dark where it goes. That's kind of fun on impact night. If everything goes to plan, about roughly 1 hour before impact would be when we first see our target Dimorphos coming out around from the back of Didymos. Remember, we've never even seen directly this asteroid before. We've seen it in a radar pulse as a kind of a pixel, bright pixel or two. We've seen the effect in the brightness of Didymos, but we've never actually seen the target. But that's when we expect to see it. And then space travel, let me just point this out, is long periods of boredom punctuated by moments of sheer terror. And this is what happened because if you, I don't know, actually, how many people watched the live broadcast on the impact night? Yeah, I did. My wife did. She went to bed, but I convinced her it was going to work, so she trusted me. Anyway, so it's only really with a few minutes before impact that we can even start seeing the shape of the asteroid for the first time. Whereas at this point, Didymos is well resolved. 2 minutes before impact, we start losing our view of Didymos because we should be locked on to Dimorphos. 20 seconds out, even the smart nav knocks itself off. Actually, at about, I think it was 30 seconds out, it stops navigating. To stop itself firing its thrusters dramatically and doing something crazy, it now is just coasting on the way in. Well, how do we know this is all going to work? I want to put this picture up because these are people that really appreciate a nice picture of the night sky. Here's Jupiter. This is from a sequence of images where the team tested the navigation software for this perpendicular phase. Because remember, what's going to happen is that Dimorphos is going to appear as a faint dot of light next to the much brighter asteroid Didymos. How do we know it's going to actually lock onto the small point of light, not the big point of light? They watched Jupiter and watched Europa come out from behind Jupiter and tested the software that way to check it would lock on a faint point of light next to a bright point of light. And it did. So it was pretty nice when a week ago on Monday we got this image at 70 minutes before it predicted impact. If you look carefully, actually, if you don't mind, I'll just switch off the lights here to allow us to see a bit better. Here's Didymos, and there's our first sight of Dimorphos. The first sight of the target. It's slightly earlier than the nominal prediction, but we knew that was probably plus or minus 10 minutes, depending on the size of Didymos, depending on its surface brightness, and so on. So that was our first sight, and we all cheered watching the NASA newscast and also seeing the images. I should say for Dark Team, we got access to all the images coming down. Oh, hello, I didn't do that, sorry. Okay, let's switch it to presentation again. There we go. You think we were cheering. Here's the view outside Mission Control. It was wonderful, wonderful. 70 minutes, we see the target. 30 minutes before impact, DART has achieved precision lock. It has locked on to Dimorphos. There it is, 2.5 minutes before impact, still 915 kilometres from this asteroid system. Remember, this is between here and here, is only just over a kilometre, with over 900 kilometres, but approaching at over 6 kilometres per second. 11 seconds away, 67 kilometres from Dimorphos. Here we are in the terminal phase, 12 kilometres away, 2 seconds away, and as I mentioned before, we took another image 1 second away, but didn't get to transmit it before the spacecraft didn't exist anymore. So let's go back to the movie, because it was great. This jiggling, by the way, when I play it, is real. That's Dart firing its thrusters to make sure it's going to hit Dimorphos. That is all real. That's it going, right, I've got to move it, bit to the left, bit to the right. People my age remember Bernie the Bolt from The Golden Shot. This is the celestial equivalent. There we go. In we go. Fantastic. So I just love watching this movie. There we go. Now, even on the way in, we were reacting. Because the first thing, all the Dart team shouted in our various dining rooms and computer labs and offices, whatever it was, it's a rubble pile! A few seconds before impact, this is our image of Dimorphos. And we had theorised, but had no proof until we got these images, that it would look like a rubble pile. A bunch of boulders and smaller bits all stuck together just by self-gravity, perhaps a weak cohesive forces between the rocks. Why did we think that? Well, remember, this is a moon of Didymos. And we have the nice theory about how those moons form. We know that over time, the effect of warming up and cooling down the surface of an asteroid can actually spin it up. And if you spin it up to just under a rotation rate of once every 2.25 hours, bits will go down to the equator and start flying off. And if you spin it up enough bits will be thrown off the equator that some of those bits will coagulate, stick together because they're all in orbit, about that large asteroid, and form a moon. And if you look very carefully, it's a very speed up animation, and it will stop eventually. There it goes, you've got a moon. Formed from just little bits of asteroid that the parent asteroid has thrown off its equator. And you, therefore, your moon should be just a weakly held together pile of rubble from the surface of the parent asteroid. There you go. For more proof, let's take a look at one of those images about 2.5 minutes before impact and look at Dimorphos. I've kind of stretched and enhanced this image. And if you look carefully, you can see that we've got a ridge along the equator of Didymos, and what looks like linear features going down from higher latitudes to the surface. So the material is flowing down to the equator, which you only need to do before being flung off. And indeed, Didymos, remember, is spinning out almost its critical rate at the moment, or around about that critical rate. So that was our reactions in a couple of minutes before impact. Now, there's only one thing in the world that can react faster than scientists on a space mission. It's the internet. So, we had great fun. So here we go. I'm sorry, I didn't say when it's coming. Please come on. For the dinosaurs! Yay! Strike one back for the dinosaurs with Dart. Here's a lovely cartoon of a quite innocent Dimorphos as Dart approaches. Now, is anybody here a fan of the clangers? Yeah, sorry about this. Here's one of the last images from Dart before impact. So we'll show them. There you go. Can't be helped. And actually, I thought the one that really made me laugh out loud, there's a satirical online newspaper called The Onion that some of you may know. And this is what they published the next day. So the point is, though, that we saw the images disappear from dark. We knew at that point, although suddenly if you listen to the YouTube commentary from Mitch Cole, you can hear somebody shout loss of signal, which means they're not receiving any signals anymore. That broken image was the visual proof that we'd hit. So then we all went, yay, we've hit. What's happening? So we've got telescopes watching the impact. Everything from the James Webb Space Telescope at the second longitude point through to all 4 8-metre telescopes combining the VLT down in Chile, although they couldn't see the impact itself, they had to wait an hour or two before it rose. So if anybody ever met Jamie Robinson when he was a student and a postdoc of mine here, he was in Kenya with a 40 centimetre, just in case it was cloudy everywhere else. And in fact, when the impact occurred, if you remember, it was just after midnight our time, here's all the telescopes that we had officially on the roster books observing the Didymos system during the impact, including those out in space, HST, JWST, and the Lucy spacecraft, which is coming in for an Earth flyby in a little while, so we can also observe it. But the important thing is that when the impact occurred, it was primarily visible from Africa, and we have a large number of telescopes in Africa observing, including the Atlas telescope that we have in South Africa. So, here's the movie that it lasts about 2 hours, this movie, and it starts with Didymos over here. Well, Didymos is amorphous, but because Didymos is so small compared to Didymos, we're really blind by the light from Didymos. Let's see if you can spot when the impact occurs, when I play the movie. Yeah, that's what we said. Or louder. So, first thing we were doing was that what we wanted to do was measure the increase in brightness, because if ejector was emitted, that material thrown into space would reflect sunlight, and so the brightness we would get would be just the brightness of Didymos plus a little bit brightness from Dimorphos, but also the brightness from the ejector. Here's the light curve I measured from those Atlas data for the first hour after impact. And if you could put this not in magnitudes, because some people want to have magnitudes, so I've just put it in terms of relative brightness. Here's the brightness before impact. That red line was put in as the predicted time of impact. I didn't put it in afterwards. That was in the code when it was running. And you can see the brightness of the system increased almost by a factor of 10. For astronomers, it went up from 14th magnitude to 12th magnitude. Now, the cool thing is that we know that most of the light from before impact was just due to Didymos. So what I can do is subtract out the light from Didymos and actually see how much did Dimorphos increase in brightness. Because Didymos is just sitting there, really, a kilometre away from the impact point. And this is it. Dimorphos increased by over 200 times in brightness. Really, really impressive. And this video shows the first thing that happened that we didn't expect to see. What we expected to see was a lot of stuff thrown out by the impact, but it should be travelling relatively slowly. Well, there is a lot of relatively slowly moving stuff that hangs around the asteroid in here, but what we've got is this very fast moving ejector. So we've got slow ejector, slow material thrown out from the impact, that's travelling not more than 10 or 100 metres per second. Actually, a lot of it will be travelling even slower than that. But then we've got this very fast ejector. And this fast ejector is travelling at 1.5 to 2 kilometres per second. Really, really, really fast. We really didn't expect that. It's a real surprise to everybody. And you wouldn't believe the messages being sent out on the chat stream while we're all watching the telescope. You go, that can't be right. What's happening? What's happening? And how bright is it? Oh my God! And wow, it was brilliant. Now, as you know, and as you may have seen, of course, we had the James Webb Space Telescope also observing it. And if you run the images together in a movie, hopefully you can see from pre-impact to afterwards. You can get something. Let me again try to switch these lights off so you can see this a little bit better. And then, I'll play the movie again. There we go. You can see that material stretched out. If you're wondering why Didymos isn't centred, Didymos is pretty much the fastest thing that either JWST or Hubble has ever followed. And they were pointing issues. We've never tried to do this before. So they got the impact, wasn't quite centred, but there's enough there to work on. Here's the images from the Hubble Space Telescope. 20 minutes after impact, 5 hours and 8 hours after impact. We can see, now you have to be careful here because we also have what we call diffraction spikes in these images. Actually, I'm going to switch that off again, there we go. So if you take a look at this last image, we've got the diffraction spikes, which is just a feature of the optical system on a telescope like Hubble, but we can also see these streamers of ejector material coming out, and if you look, you may see how they change over the first 8 hours after impact. Now, all these images are fantastic, but even with Hubble Space Telescope and even with the James Webb Space Telescope, Dimorphos and Didymos are too close to see separately. They're a single point of light. Luckily, we had this on board DART. The Italian Space Agency's QUB, which stands for Unlike Italian CubeSat for Imaging of Asteroids. Well, it's got an image too, which is good. And the QUB was designed, proposed very quickly by the Italian Space Agency when what it was known here wouldn't be there for the impact. It was carried by DART and released on September the 11th. So 15 days, roughly 2 weeks before impact. And on a trajectory so that it would fly about 55 kilometres from the asteroid system 3 minutes after DART hit. And hopefully you've seen some of these images. Net surprise. We did not expect to see this kind of stuff happening in the QUB images. And there's still much discussion in the investigation team about what happened. But one can see the streamers coming from the impact. I should explain that these are from two different cameras. The QUB had 2 cameras, a high-powered camera called Luke, a high-powered camera called Leia, you get the idea, and a lower resolution but multicolour camera called Luke. So Luke and Leia provided us with our first close-up images of a planetary defence experiment. And just looking at this image here from, you can see the streamers of ejector. This is just 2 minutes after the DART impact. We are still downloading the images. The QUB took over 600 images of the impact. Only about half of them have been downloaded to Earth. Its downloads are occurring every day still. So, lots of surprises from the impact. There's one thing that didn't surprise us. We got a tail. Here's an image taken in New Zealand, and it's a combination of images taken between 13 and 18 hours after impact. Well, we can see the material streaming out, but we're also seeing the growth of a tail from the asteroid system. And this had been predicted. Here's the paper that predicted it, that was published earlier this year. And this is simply a tail of small particles of rock that forms exactly the same way that the dust tail of a comet forms. Radiation pressure, the fact that sunlight is reflecting off really small dust particles, when that sunlight reflects off them, pushes those dust particles in the opposite direction, and you get a dust tail. But instead of a comet, we've got it with an asteroid. Now, that's the tail going. What about these other streamers here? Well, let me take you back to another impact on an asteroid that occurred in, was it 2018 or 2019? 2019 I think it was, because the Hayabusa 2 mission to Asteroid Ryugu from the Japanese Space Agency was a sample return mission. What they wanted to do was collect samples from the subsurface. So what they did was they manoeuvred Hayabusa 2 up here somewhere and dropped a shaped charge. Then it went around the back of the asteroid to not get injured in the subsequent blast from that shaped charge, but deposited left behind it a little camera, free floating camera. And these are images from the camera. Here's where that shaped charge is going to hit the asteroid. Here's a blow up of it. It's a 2 kilograms mass travelling at 2 kilometres per second. There you go. So if you, this has got a loop around. So if you look over this side, you can see from the drone camera how a crater is formed on the surface. And if you zoom up here, this maybe gives you a little bit better impression. Because when we form a crater, not everything comes out at once. The shockwave has to propagate through the asteroid. And so you basically grow the crater from the inside out. And as you do so, you get this cone of material shot out. Here's what we're seeing in the images. So what I've done is I've taken this image of, if you can see Dimorphos and Demos from Earth, you can see how dark it came in to hit Dimorphos. It came in this way, and if you want to form a crater, that ejector cone will go like this. And that's what you've got here. We're seeing the ejector cone from that cratering process on Dimorphos. And it was great because we could actually watch that ejector cone, but also the tail grow. Here we've got images from about just over 24 hours after impact from Atlas. We can see the tail growing as we watch it. It's absolutely lovely. And I know that the SOAR telescope, 48 hours impact, released this beautiful image of Dimorphos and Didymos being in here. Here's these streamers from the ejector, and here's this beautiful long tail stretching out now over, I think this is 10,000 kilometres from the asteroid system. So, needless to say, it's been a busy week and a half. We are still working on the data. We're still collecting data in QUB. Here's images from Sunday of the Dimorphos system, from Atlas. I was going to show you one of them today, but it's cloudy. Well, the telescope was supposed to image it, so maybe we'll get some more tomorrow. But the image you can see, the Dimorphos moving across the sky with a beautiful tail. You can see faintly here in these images, and the smudge of material that's still moving outwards from the system. What's next? Well, what's next is measuring the orbit change, because we know before impact that Dimorphos was going around Didymos once every 11 hours 55 minutes, and we can measure that from Earth, from the light curve, from how brightness changes. Now, one day after this, if we could measure it in all that gunk thrown up from darts, we might start seeing a small shift in the position of Dimorphos. But probably, well, at that stage, we won't be able to, because there's so much debris in the system as we've observed, we wouldn't be able to observe it. But also, it's only going to be a small shift. So what we need to do is just wait, because if it's given a kick, then over time, the position of Dimorphos before impact from our predictions and afterwards will change, so that eventually we're kind of almost 180 degrees out of sync. And when we do that, we'll be able to measure precisely this period change. But here's another thing. What happened to Dimorphos? Well, we think it's still there. In fact, it should be still there, because we know the kinetic energy of DART was 10 times less than the binding energy of even a rubble pile without any strength the size of Dimorphos. So I can't have ripped the moon asunder, but my God, we hit it hard. So, beginning of the year, Sabina Radican and Martin Jutsi did some simulations as to what would happen to Dimorphos if it was a bubble cloud. So in these simulations, this is 2 hours after impact, the original shape of Dimorphos is given by the grid, and the eventual shape of Dimorphos after we hit it with DART is given by the solid bit. We didn't know even the shape of Dimorphos before we got there. We only knew the rough size, 160 metres. But it just shows you that we know how if it's a sphere, an oblated ellipsoid or prolated ellipsoid, we were Dimorphos wouldn't be the same shape afterwards as what we found it. And in fact, that's why Dimorphos was called Dimorphos, Greek for two shapes or two faces, because we have the shape of Dimorphos before the impact and the shape of Dimorphos after the impact. But we can't see this from Earth. So here comes Hera. We're going to launch in 2 years this month. It will be later on in October. There will be the 2-year mark. And we will arrive there at the end of 2026, to be honest, it's going to be in all probability January 2027. And unlike DART, which just flew out the system at 6 kilometres per second, Hera will rendezvous. And we'll spend up to a year there, not only making measurements itself, but also using 2 CubeSats, Milani and Juventus, which will measure the properties of both Didymos and Dimorphos, because this is the important thing. We've carried out an experiment in space to see if we can move an asteroid. How do we move an asteroid that isn't Dimorphos? We need to know exactly how Dimorphos is put together, or was put together, and what its structure is, what the materials that it's made of, so that we can put that in our models, and we change our models until we get the answer of how much you would move Dimorphos according to our model with what actually happened with the DART impact. And then we have an anchor point that we can apply to future asteroids if we get those calculations correct. So that's what's coming. In the meantime, I was on asteroid duty last week, apart from teaching and DART and everything else. And just over 24 hours later, I found this guy. 2022 SE37 with the Atlas program. It's actually about 400 metres across. We don't know, we haven't measured it, but it's probably roughly it's over twice the size of Dimorphos. Now, the good thing is that the distance for this one is 21 million kilometres last week, and it can't get much closer than that. It was on a very close approach to its orbit. So we're safe from this one, but there's going to be one out there. So what comes next is not just Hera. We have to find those objects with our name on. So we have, of course, the Rubin Observatory, which will start its survey in just 2 years' time, the world's largest digital camera. And part of its main role is to find small near-Earth asteroids down to the size of Dimorphos and even smaller, and make sure we know where they're going. Hopefully, in 2026, if it passes its review next year, we'll have also NEO Surveyor, a NASA infrared survey telescope, which will also be surveying near-Earth space with small asteroids. And if telescopes are fine for you, but you just want more close-up and personal images of asteroids, we're going to have that as well. We have 5 funded missions to near-Earth objects launching in this decade. We have near-Earth asteroid Scout, which should launch next month. Why? Because it's sitting on the pad with Artemis 1. Didn't go up, as we all know, last month, but it's a solar sail mission. And it's NASA's first interplanetary solar sail mission that, if it can still reach it, I don't know what the latest trajectory calculations are, but if it can still reach its targets, it will reach the near-Earth asteroid 2020 GE in 3 years' time. We have Osiris Apex. Now, this is the Osiris Rex mission repurposed. It's on its way back to Earth, and it's going to do a flyby of Earth next year and deposit its sample of the asteroid Bennu and bring it back to Earth. and then it's going to carry on, because in 2029, it's going to rendezvous with the asteroid Apophis, just after it does its very close flyby to Earth on Friday the 13th, of course, of April that year. Apophis is one of the most dangerous asteroids that we know of, potentially dangerous asteroids in near Earth space at the moment, and as I say, this is going there. Janus, not sure. Janus is again a satellite that's been launched with another asteroid mission called Psyche. It was due for launch this year, but it didn't make it. And it was originally got, this is a twin satellite mission to rendezvous and will fly by with two near-Earth asteroids. Because that launch has been changed, we don't know which asteroids it's going to be repurposed for now. But the spacecraft are basically sitting there ready to go. So we're not sure when they're going to get to a near-Earth asteroid, but they will. Destiny Plus from the Japanese Space Agency will launch the same year as here, in 2 years' time, 2024, and it's going to go past the mysterious near-Earth object Phaethon 4 years later in 2028, plus maybe a couple of other near-Earth objects as well. Phaethon, if you don't know, is the source of the Gemini meteor shower, which we enjoy every year, if it's not cloudy. And then finally, I had to put it in, Comet Interceptor from the European Space Agency will launch in 2029 and will sit out there waiting for a comet to intercept. And the important thing is that, because of the mission design, when it picks its target, that comet must come close to the Earth's orbit. So whatever comet it intercepts in the next decade, it will be a near-Earth comet. And all of this doesn't even include here. So lots of stuff happening. So here's my summary from the talk this evening. First of all, DART has been demonstrated clearly and spectacularly our ability to perform a kinetic impactor intercept. The laws of physics tell us that Dimorphos has been deflected and is now in a new orbit, but we've got to measure that. We've got to measure that new orbit. The more of a deflection, the more of an intercept there will be, the more deflection there will be. Just keep watching the news. The team will announce a deflection as soon as it's clear and it's agreed upon. There's no ambiguity. Those measurements have already started trying to measure this deflection, both from optical ground-based telescopes and also from radar. There's still lots of data coming in, lots of work still to do. Sorry, I had more late nights, but I've got more stuff to do still for the next weeks, months, years. Hera, it's all about years. Hera will launch in 2 years' time. We're going to go back and actually see what did we do to poor little Dimorphos. And of course, we're still looking for that next dangerous asteroid, that next impactor, to make sure that we, and hopefully by that stage, we'll be able to apply the lessons of DART to that object. But there, I'm going to finish. Thank you for coming along this evening, and thank you for your attention.
Alan, thank you very much indeed. That was both exciting and fantastic. Thank you very much indeed. Ladies and gentlemen, I'm sure most of you realise that we've been very privileged here this evening to get this information about something which has raised so much popular attention, so much media attention, and to hear it from one of the lead scientists on the mission. So I think, Alan, you need to be congratulated from your own home territory here.
Thank you. Can I just say one thing? I mean, it's always easy for me, there's one person standing in front of you wearing the t-shirt. All those years of work, all those months of work, you get a few